instructor copy for facilitated diffusion and active transport are online now, so you can see those slides as well. All right, so let's concentrate now on action potentials. All right, get this going. Okay, so now what I want you to think about is what's happening at the axon hillock region. All of those different graded potentials are summed in time and space, and they all arrive at the axon hillock. All that needs to happen is a 15 millivolt depolarization, right? It goes from minus 70 to about minus 55. And if that depolarization reaches threshold at minus 55, then you're going to get an action potential that's going to propagate all the way down the axon to the axon terminal end. So where you can think about graded potentials as being very analog, kind of analogous to an analog circuit, right, where there's a lot of gray, this is an all or none response. It's either on or off. It's digital. If it reaches threshold, then it's on, and it goes all the way down the axon. If it doesn't reach threshold, then it doesn't happen. So it's just all or nothing. So you can see that the initiating stimulus, right, it could be minus 55, but it could be so strong it depolarizes to minus 20. It doesn't matter. All you need to do is reach minus 55. That's it. So the strength of the stimulus is independent of the response. You just need to reach threshold, and you can see the amplitude of the response is always the same. Okay? All right, so these four action potentials, each are the result of a stimulus strong enough to cause depolarization. That's shown in the right-hand part of the figure. Okay, now we actually talked about this before. I showed you this particular animation when we were talking about facilitated diffusion, but we were concentrating on the voltage-gated sodium channel. What's happening here, what initiates those action potentials, are the stimulation of voltage-gated sodium channels. Unlike graded potentials, which are ligand-gated, these are voltage-gated sodium channels. And threshold is the depolarization that's required to open up these voltage-gated sodium channels. That's the definition of threshold. It is the, I'll say that one more time, it is the voltage required to open voltage-gated sodium channels. And that's what initiates action potentials. So let's put this all together. Why did you learn about equilibrium? Oops, I'm sorry. Why did you learn about equilibrium potentials, right? When you open up those voltage-gated sodium channels, you're going to change the relative conductances, where now it's going to be about 90% of the total conductance is due to sodium, and only 10% is due to potassium. What is that going to do to the membrane voltage? Think about the chord conductance equation. What is that going to do? 90% of the total conductance is due to sodium. Where is the membrane potential going to go? Yeah, it's going to become much more depolarized. So I'm going to say it this way. It is going to pull the membrane potential closer to the equilibrium potential for sodium. Right? It's going to pull that membrane potential closer to the equilibrium potential until it gets to be about 9/10 of the way between the equilibrium potential for sodium and the equilibrium potential for potassium, right? So let's take a look at that, right? What happens when you reach threshold is the voltage-gated sodium channels open. It pulls the membrane potential closer to the equilibrium potential for sodium. Then the voltage-gated channel inactivates, and it's the depolarization that actually opens up a potassium channel. This is called the delayed potassium channel. So what that happens is sodium channels close, the delayed potassium channels open. That is a second population of potassium channels that now pulls the membrane potential back down closer to the equilibrium potential for potassium. It actually goes even more negative, even more hyperpolarized than the resting membrane potential, because there's two populations of potassium channels open. And then when these delayed potassium channels close, that's when it goes back to 90% potassium, 10%. Here you could probably predict the total conductance is about 95% potassium, only 5% sodium. Here's where it's back to 90 and 10. 90% potassium, 10%. Pretty good? So I really like this animation. If you want to see it live, you can actually go back to this link. Just copy and paste it and you can see it's on a loop. It'll just show you what's happening. But this is the ionic basis to the action potential waveform. This is due to these voltage-gated sodium and potassium channels opening and closing that is giving you the action potential waveform. And this is what Andrew Huxley and Alan Hodgkins actually elucidated, made clear. This is their contribution to action potentials, to neuroscience. All right, so for those students that like more visual kind of representation, this is a nice diagram, but for more students that like text and, flow charts, you can go through this. It's saying the same thing. Okay, so let's go back to, you can play around with this as well on this nerve simulation, but I want to show you how you can manipulate that action potential waveform. Okay, so this is something that you don't have on the site, on the video, on Canvas. Let's do a little bit of review. I want to give you an orientation. This black line is the action potential in the squid, right? If you were to run this computer simulation, this is what you would find. You would reach threshold. A graded potential coming into the axon hillock region would cause a slight depolarization. All you need is that 15 millivolt depolarization event, which opens up all of those voltage-gated sodium channels, pulls the membrane potential closer to the equilibrium potential for sodium, and then these voltage-gated sodium channels inactivate, and the voltage-gated potassium channels come on board, pulling the membrane potential back down towards the equilibrium potential for potassium. Then those delayed potassium channels close, and that brings it back to rest. So here's just some, you guys know this already. The equilibrium potential is the membrane voltage required to keep potassium from moving down its concentration gradient. Equilibrium potential for sodium, membrane voltage required to keep sodium, the net movement, moving down its concentration gradient. All right, these two traces are giving you some information about conductance, right? As the conductance for sodium rises, it's going to pull the membrane potential closer to the equilibrium potential. Here's where the delayed potassium channels open, so sodium channels inactivate. You can see that trace go down, and the depolarization activates the delayed potassium channels, so you can see their conductance goes up. Conductance is the ease with which ions move across the membrane. Threshold, by definition, is the membrane potential required to activate voltage-gated sodium channels. And then, this is something I get a lot. This is a definition you do know for the exam. You'll need to know. This is a term called the overshoot. The overshoot is the difference between the peak action potential and 0 millivolts. So everything over 0 millivolts is called the overshoot. Pretty good with that? All right. The undershoot, or what's known as the after hyperpolarization event, is the difference between the most negative action potential and the resting membrane potential. So I'll go back to this one. It might be a little bit easier for you to see. Okay, so the undershoot, or the after hyperpolarization, is the difference between the most negative part of the action potential and the resting membrane potential. This is called the undershoot, or the after hyperpolarization event. It's due to that second population of potassium channels that come on board, that pull that membrane potential even closer to the equilibrium potential for potassium. All right, just some terms that are important for the exam. Let's play a little game. You guys can talk about this within your group. This is a cool simulation. Like I said, it's nerve.uchicago. And it's giving you can actually enter in the extracellular sodium levels, intracellular sodium levels, potassium levels, and then you can add a few toxins, okay, to, manipulate that action potential waveform. So here's what we got. We've got our action potential waveform. We can also manipulate the radius of the axon, the diameter, the conductance for sodium, internal resistance, we talked about that with the length constant, max leak channel, and temperature. So first, what I want to do is I want to change the temperature from 6.3 to 2.5. That's the first thing I'm going to do. How do you think that's going to change the action potential waveform? So talk about it in your group. What do you think? How is that going to change the action potential waveform? I'll give you a hint. Think about enzymes. How do enzymes work when you vary the temperature? Yes.
Perfect, thank you.
Sure. Yeah. Anybody need an extra sheet? It's up here.
For the higher conductance, does this make the action potential higher?
Yeah, so if you're talking about the higher conductance of sodium,
Okay.
yeah, it's going to pull the membrane potential up,
Okay.
yeah,
And then
towards the equilibrium
if it was
potential.
potassium?
Then it's going to pull it back down towards that equilibrium potential for potassium.
Close
So
to
yeah, so that's why it's important to know the equilibrium potential, because it kind of tells you what's going to happen when you open up those channels and increase conductance of that particular ion.
Okay.
Again, it'll pull it towards the respective equilibrium potentials.
Okay.
Yeah.
I have a question. So for my top hat, I didn't get any points for the first one.
Okay.
But I did it from my phone
Okay.
at that time.
I trust you. I believe you. Can you send me an email and I'll change that?
Yeah, thank you.
Yeah. Sure. All right. What ideas do you have? Well, how is temperature going to change the action potential waveform? What do you think? Anybody want to take a wild guess? What's going to happen to the duration? Yes.
Generally, I'm not sure about the duration exactly, but I know just generally when you have lower temperatures, enzymes are temperature specific, so they'll either be inhibited itself, so it won't be function at all, or be reduced function.
Yes, it'll slow, right? So what would you predict then if you increase the temperature?
It might increase for them
Yes, okay. Let's just kind of go under the assumption as you increase temperature, you're going to speed up the function of these channels. Okay. All right. I'm going to go with that, yes. So what's going to happen is it's going to activate faster, inactivate faster, and close faster. It's going to shorten the duration, right? This is what it was before. And you can see now that it's working so much faster, the duration of the action potential waveform is really reduced. It's much, much quicker. All right, so let's try another one. And don't forget, with the temperature variable, if you change temperature, it is going to change the equilibrium potential slightly. Remember, that's built right into the Nernst equation. So, want to make sure. All right, how about this one? Pronase. We're actually going to increase pronase from 0 to 135 micrograms per mil. What pronase does is it's an enzyme that cleaves, just cuts off that inactivation gate. What's going to happen to the action potential waveform? You can talk about that on your table. What if you clip off the inactivation gate? What's going to happen to the duration of the action potential waveform? All right, we're kind of running out of time. What do you think? What happens if you clip that off? What happens if you clip that off? What's going to happen to the open state of the voltage-gated sodium channel? I saw that. It's going to be much longer, right? So what's going to happen to the action potential waveform if it's in its open state much longer? It's going to prolong that action potential waveform. I would even argue that the peak is actually going to be much higher, right? I would argue that. So that's a limitation with this program, I think. But here's where it was before. You can see that the duration of the action potential waveform is much longer. And I would, again, argue that it's probably the peak is higher as well. All right, we're going to skip this one and go to this one. Tetrodotoxin. Maybe you all have heard about this. Tetrodotoxin is a toxin that completely inhibits the voltage-gated sodium channels. It can be isolated from this genus. This is a puffer fish. The genus is Fugu, right? And this toxin accumulates in its ovaries and other parts of the fish. Basically, with sushi chefs in Japan, they make sushi out of this fugu, and they have to make sure that they only get a very specific amount of tetrodotoxin. So what do you think is going to happen to the action potential waveform if you add tetrodotoxin? And I'm talking, this is potent stuff, 5 nanomolars. What's going to happen? We're running out of time, so I'll just tell you. It completely inhibits the action potential waveform. Let me just tell you again, if the sushi chefs don't prepare this properly, and if they do it properly, it makes your tongue tingle. But if they give you too much tetrodotoxin, it completely inhibits the respiratory neurons. You suffocate and die, okay? So I would say if you're in Japan, you should learn how to say, hold the tetrodotoxin, please. All right. We'll finish this up. We only have about 5 or 10 more minutes of this lecture. We'll talk about neuromuscular junction another 10 minutes, and then we'll review. Have a great weekend, study hard, and I'll talk to you on Monday.
I don't know if you saw. I don't think you saw the email because I think